Evening, everyone. So, welcome to our chemistry live stream. What we're going to be doing tonight is going through all of the work that could come up on the paper one for chemistry for OCR Gateway specifically, but there is quite a degree of overlap between the OCR Gateway and other specifications for this particular paper. So, if you're doing a different exam board, there's still going to be a fair chunk of stuff that is going to be the same for you as well. As before with the biology, we're going to go through everything that could come up on the combined and the triple papers, higher and foundation. I will try to remember to flag up those different bits as we go. We do have the chat running, which does mean that if there are any bits that you'd like to ask questions on, then by all means feel free to post a question in there and I will do my best to spot it and obviously answer that for you as we go. Right, this one should be about 90 minutes usually, so let's make a start then. So to start off with, we're going to start with the lovely short topic that is C1. Now, the nice thing about C1 in the OCR scheme is it's basically going back to year 7. So they ease you in very nicely to the chemistry here. Because what we're going to start off with is that idea of the particle model. Now, the particle model, quite simply, is how we're actually going to explain the movement of different things by creating something that's easy for us to understand, because trying to imagine atoms themselves, not easy. So we make it into an easy to understand thing called a model. Now, when we're looking at the particle model, then the first thing we need to know is that we can use this to explain a couple of key properties. First one is if we can actually compress things. So as far as compressing states of matter goes, you can compress a gas, but you can't compress a solid or a liquid. Reasons for that: between every particle in a gas, there is all this space. So we can obviously move the particles closer together. But when it comes to a solid or a liquid, they don't have that space between them, so you can't make them any closer. So you can't compress a solid or a liquid, you can compress a gas. Second one is all about their ability to flow. So gases and liquids can flow, so they can move from one container to another quite easily because the particles are able to move over each other. But solids cannot flow because those particles are held in those fixed positions, which means they don't really flow anywhere. They just kind of fall as a lump. Now, hopefully these little diagrams are familiar to us from going back to year 7. We have the arrangement of particles in a solid where they are in these lovely regular rows. They are also all touching, so they're very close together. And in terms of their movement, then they just vibrate around a fixed point. Liquid is the next one. So you can see they're all very close together still, but they're no longer in those nice, neat, regular rows. They're a little bit more random in their arrangement. And in terms of how those particles are moving, they're able to flow over each other. Then at the bottom, we've got our gas, randomly arranged, very spaced out from one another, so lots of space between them, and they're moving very quickly in all directions. So if you get any of those questions that they always flag up that they want you to talk about the particle model by basically saying, use ideas about particles in your answer, this is what we're talking about. So we need to be talking about their arrangement and their movement. So basically just have a little look at those questions. As soon as you see use ideas about particles in your answer, this is where we're going, particle model there. Now, the next thing we need to understand are two different types of change that can occur with our chemicals. We've got physical changes and we've got chemical changes. If we're talking a physical change, this is a change in the state of matter. So quite simply, we are going from a solid to a liquid to a gas, or vice versa. Now, in terms of our physical change, these ones are going to be the reversible ones. Think about stuff you know. If you've got some ice and it's melted, you can just stick it back in the freezer and get ice again. So they are reversible changes. And we're not making any new substance. So we start with water in solid form, we still have water just in the liquid form. So these are our typical kind of melting, evaporating, condensing, etc. They're all physical changes. Our next one, the chemical change, this is where we are going to produce some kind of a new substance. So because we're going to have a chemical reaction making this new substance, that means these tend to be irreversible. So go with the old favourite of burning something. If you light a match and you've burnt it into a pile of ash, you can't recreate that match. So what we have there is a chemical change. It's irreversible. And what we're making, new substances, and they can have very different properties to the actual reactants, the things we started with. So those are some of the real basics for us to start off. The higher tier folks, and this is higher tier combined and higher tier triple, need to know about some of the limitations of this particle model that we've created. And basically there's three to know. First one, we're not actually taking into account anything about the forces between the particles. We're not taking into account the size of those particles or the space between the particles. So if they ask you to name or list one or two of those limitations, go with any of those. We're not being told about the forces, the size, or the space between the particles. So really straightforward to pick up those marks. That's the only higher tier bit on C1. So there you go. 3 little simple points to remember on the higher tier there. The last bit of the C1 topic is all about the structure of atoms. Now, before we delve into this, there's a few key words that we should know the meanings of. So the first one is the word element. Now, elements are the simplest form of any substance, okay? So basically, these are the ones we find on the periodic table. Now, you are not going to find a compound on the periodic table. Please don't spend your time in the exam sitting there looking to try to find things like water or carbon dioxide, anything like that on there, because you know what? They're not elements. They're not on there. You're wasting your time. This should finish around 7:30, folks. Now, when we're talking about an atom, that is the smallest particle of any of those elements. And if we've got a molecule, this is where we've got 2 or more atoms that are chemically joined together by some kind of a bond. And we'll look at the types of bonding a bit later on in a later topic here. Now, what we actually need to remember then is that when we're looking at the length of those typical bonds between atoms, then these are usually given as 0.1 nanometers, or you could write that as 1 × 10 to the -10 meters, okay? Right, structure of an atom. Here we go. This picture is hopefully super familiar to us. This is just the typical structure of an atom diagram we need to know. So what we have, this little thing in the middle, that is the nucleus made of protons and neutrons. We then have these shells around the outside, sometimes called orbitals, which contain the electrons. Now, because we've got all of those protons and neutrons in the nucleus, that means we're going to have a positive charge on the nucleus as well. It's also where most of the mass of the atom is too. Now, the reasons for that is because hopefully we all remember this lovely little table that you've probably all got in your chemistry books, which has those 3 subatomic particles in there, proton, neutron, and electron. You then hopefully have 2 facts about each of them. That is their relative mass and their relative charge. So when we're thinking about the proton, their relative mass is 1 and their relative charge +1. Neutrons, relative mass is also 1. Their relative charge is 0. Okay, neutrons, they're neutral, they have no charge. And then finally, the electrons, these are 0.0005, or you could write that as 1/2000. Whichever way you prefer, absolutely fine for the mass. In terms of their relative charge, -1. Make sure you do include the plus and the minus for the proton and the electron, just to make it explicit what the charge is that you're talking about there. So because our nucleus has protons, positive charge, neutrons, no charge, it is positive overall. Watch out for that, and they sometimes throw that in as a little 1 marker. Now, we then need to come on to understanding our next little bit, which is about how to use the periodic table to find the numbers of protons, electrons, and neutrons. Do remember, you get this, okay? This is the exact periodic table you get in your exams. So you will have a copy of this. Please get it out and use it. It's not just a piece of paper to look pretty in there. Now, OCR is super nice because if you look up here, this is a key. Now, you don't have to know what these two numbers in the boxes actually are, because they tell you explicitly right here which number is which. So I see it as one of those unforgivable sins if you get them wrong in the exam, because it's printed right there, folks. They're giving it to you. So the two numbers on the periodic table. First one, the atomic number. Now, the atomic number is going to be the number of protons, and that is identical to the number of electrons. So if you're asked to work out the number of protons or electrons in any element, as long as it is a neutral atom, you just copy the atomic number from the periodic table for both. It's the same number in each case. The second number, the mass number, this is the number of protons plus the number of neutrons. So what you actually need to do there is to find the number of neutrons, mass number minus the atomic number, because all you're left with there are the neutrons. The one to watch out for on this one, if they're neutral atoms, then absolutely just write down your atomic number for protons and electrons, and then for your number of neutrons, mass minus the atomic. If they give you an ion, then you're going to have to look at your electrons more carefully. So same thing applies for the protons and the neutrons, but with the electrons, depending on the charge on that ion, is going to change how many electrons there are. Okay, it's not going to be the same as the protons. So if you've got an ion with a +1 charge, then your number of electrons is going to be one less than the atomic number. If it's a -2 charge on the ion, then just add 2 electrons onto the atomic number, and that gives you that. So nice and straightforward to work it out. Just watch out for the ions, because they throw them in occasionally on those little tables they get you to complete. The next definition we need to know is isotope. So 2 ways that you can get this defined in the exam paper. Okay, this can be up to 2 marks, so it's a good definition to know. First one is that it's an element with the same number of protons and electrons, but a different number of neutrons. Or you could phrase it as that it's got the same atomic number, but a different mass number. Either of those is absolutely fine for the explanation of an isotope. It's the neutrons that change, nothing else. Okay, so protons and electrons always the same, only the neutrons are going to be changing here. Now, we do mention this word ion a fair bit, and that's just a charged particle. So we're going to basically form these ions by either gaining or losing electrons. If we gain electrons in the atom, it becomes a negative ion. However many we gain is the charge. If we lose electrons, it becomes a positive ion, and again, however many electrons we lose gives you that positive charge there. So the last thing we need to know here before we move on to C2 is the names of those scientists and what they actually did to come up with all of this structure, okay? So we need to know the first scientist is Dalton. No one cares the years or their first names. Surnames, absolutely fine. Basically, surname and discovery is all we need here. So Dalton was our first guy, and his whole thing was that atoms are tiny, indestructible spheres. So all atoms of the same element are going to be identical to one another, but they are basically these tiny, indestructible spheres. Scientist number 2 is Thomson. His contribution was the electron. He discovered it, this little negatively charged particle. And once he discovered it, he came up with this model called the plum pudding model. So that's basically where we have this big positive cloud, and scattered amongst the positive cloud, we then have these little negative, let's turn it that way, these little negative electrons. So that is our plum pudding model there, the positive cloud with negative electrons scattered through. That's what Thomson gave to us. Third guy is Rutherford. He did work with a couple of our scientists, but no one remembers their names, Geiger and Mazda if you want to know. Now, his experiment was all about having this thin sheet of gold foil, and then he fired these things called alpha particles down. If the plum pudding model had been right, they would have just gone straight through, because it's just this cloud. However, they didn't. What happened was they were bouncing back at different angles. So they were hitting something in the foil itself. So he then came up with this idea that there must be this positive nucleus that contains most of the mass of the atom. And that's what was causing the electrons then, not the electrons, sorry, the alpha particles to bounce off. The electrons, he said, are orbiting like the planets. So this was our planetary model of the atom. That stayed around for a little bit, and then we had Niels Bohr. So Bohr is our fourth and final scientist that we need to know for OCR. Did a bunch of maths and basically said those electrons, they're actually in these fixed energy shells. And that's what we still use today. So when we're looking at our little diagram here, this is the culmination of all of those scientists' work. So each time they did something, they would have published their work so that others could learn from it, build on it. And of course, that allows for that peer review, that idea of being able to look at another scientist's work, check it, make sure it's true, and then develop those ideas too. So that's C1. That's all there is to it, just a little bit on our atoms. Next up, we are coming on to C2. So first thing that we've got in C2 is a calculation that I would say you are guaranteed to have to do on your exam tomorrow. Relative formula mass. And it's a nice calculation. It's adding. So when we need to work out the relative formula mass, whenever they give you an actual formula, so they're going to give you some kind of a chemical formula and then ask you to work out the relative formula mass for it. Let's just do water today. So if we've got our formula there, H2O, and they want you to work out the relative formula mass for it, then what we need to do, use our periodic table. Look up the hydrogen. We're going to find that hydrogen has a relative atomic mass of 1, and there's 2 of them, H2. We then look up oxygen. That's got a relative atomic mass of 16, and then you just put it together, add it up. So 2 hydrogens, so 2 times 1, and then we add our 1 oxygen at 16. Gives us 18 as our total there. That's literally all you need to do for relative formula mass. The only way they can make it more complicated is by sticking something in brackets. So let's do this one. If we have something like that, where we've got some bits in brackets and other bits not, this little 2 down here means that everything in brackets is times by 2. So we've got 1 magnesium, 2 oxygens, and 2 hydrogens. As long as you remember that, look up your relative atomic masses and then add them together. Don't forget, use a calculator. Stupid errors do occur whenever we are doing things in a high pressure exam situation. So even if it seems really obvious and you can do it in your head, double check it on the calculator to be really certain. You will have time in this exam, so don't panic about running out of time because you're using a calculator to double check. The second thing we need to be able to do is work out this thing called the empirical formula. Now, the empirical formula, quite simply, is the simplest whole number ratio of the atoms of each element in a given compound. So if we have a look at something that's hopefully familiar to us, there's glucose, C6H12O6. To work out the empirical formula, we need to find the highest common factor of all of those numbers. So in this case, 6 and 12. So the highest common factor of 6 and 12 is 6. And then all we need to do is divide each of those by 6. So 6 divided by 6 is 1. So we just write C. 12 divided by 6 is 2. So it's H2. And 6 divided by 6 is 1. So the empirical formula just becomes CH2O. All you're doing there, highest common factor, divide each of those atoms by the highest common factor and write down whatever you get. Okay, simplest whole number ratio. Now, the next bit of C2 is all about purity and separating stuff. So, first thing, a pure substance is one that consists of one single element or compound. So there is only one substance in that particular thing. If we're talking impure, this is where we have more than one element or compound present. These are where we're going to start to see the word mixture come in. And when we're talking about a mixture, this is where we've got more than one element or compound that are occupying the same area, but they're not chemically bonded together. So they're mixed together, not bonded together. So the air you're currently breathing in, for example, is a mixture of oxygen, carbon dioxide, nitrogen, etc. They're all individual molecules, not chemically bonded together as a giant thing. Now, one of the questions they do quite like to ask is how we can actually identify if we have a pure substance. And the simplest way is through the melting point. If we've got a pure substance, then it will melt at one single sharp temperature. So what we mean by that is that if you slowly heat it up, then what we're going to find is it changes from a solid to a liquid at just one temperature, say 40 degrees. If it was impure, then what would happen is it would melt over a range of temperatures. And what we actually find is that the greater the difference in temperature that our substance melts at compared to what we expect it to melt at, then the more impurities there are present. Okay? So think about how we're going to do this actual experiment. If we're talking about the practical side of this, then we need to heat it slowly. Okay, you're not going to whack on the blue flame on the Bunsen burner underneath it, because otherwise, how are you going to know what temperature that's melting at? And we're going to stir it to ensure that the whole sample has that heat evenly distributed through it. Okay, so heating slowly, stirring it as it goes, and that gives you your melting point. If it all melts at one temperature, it's pure. If it doesn't, it's impure. Right, our separating techniques section. We've got a whole range of different separating techniques we need to know, because they can ask us things as simple as draw the line to the picture, but they could also ask us up to a 6-mark question about how we could separate 3 different substances based on properties they tell you in a table. So you need to know these separating techniques pretty well. First one that we're going to look at then is going to be filtration. And before we really delve into this, there's a few words and terms that we need to understand. First one, solution, which is where we've got a solid dissolved in a liquid. Okay, so the solute dissolved in a solvent is another way we would say that. The solvent is a liquid that will actually carry out the dissolving process. The solute is the solid that becomes dissolved. And then we have soluble, which means something will dissolve, or insoluble, that it won't dissolve. Okay, so make sure you do know those key words and what they actually mean so that you can understand a table of properties about them. So filtration, first of all. Simple picture, you'll recognize it nice and easily if it crops up, because it's got a bit of filter paper at the top here sitting in a funnel. So quite simply, we've got a little conical flask, we've got a funnel with a bit of filter paper sitting in it, we pour our mixture in the top here, and then we're going to separate it out. If we have got a mixture which consists of an insoluble solid and a liquid, okay? So we use filtration to separate out the insoluble solid from the liquid, because that sits in the filter paper and the liquid just trickles through. The way it works, filter paper just has these teeny tiny little holes in it that are small enough to allow the actual liquids to pass through, but they're not large enough to allow the bits of the solid to pass through. So they stay basically at the top as the residue. So that's our first one, is filtration. Number 2, crystallization. Now, crystallization is where we actually want to get the solid from the dissolved solution. Okay, so if we've got a solution here, think salt water, then what we're wanting is the salt here. So what we do is we put a little evaporating basin on top of a beaker of water over our Bunsen burner, and we're going to heat it gently. That's why we've put the beaker of water here, is to allow it to heat gently rather than directly heating the evaporating dish and leading to lots of spitting. So what's going to happen here as we heat up, we're going to evaporate off the actual liquid, and we will just be left with the solid at the end. Now, generally, the best practice for this is that you're going to heat it for a little while, and you will know when it becomes saturated, okay? And by that, what we mean is when you look at it in the actual evaporating dish, you're going to start to see little crystals starting to form. At that point, you turn off the Bunsen burner. The reason for that is that if it's a saturated solution, then when the temperature drops, when we're no longer heating it, then it's going to actually decrease the solubility of the solute. So more of it then separates out as it cools away. Now, what we might be asked, linked into this sort of question, is how you can create a pure dry sample of something. So we've got the pure because we've got rid of the other thing, but the dry bit don't miss that out, okay? In order to get the dry part of this substance, all you're going to do is take those crystals and place them in a warm oven. That's it. It's the easiest thing in the world, and yet so often people forget that bit. So if you see pure, we're going to use a separating technique to get it to just the one substance. Dry, stick it in a warm oven. Our third technique is simple distillation. So here is our simple distillation setup. You've got your little flask here, which connects into this device called a condenser. Now, quite simply, we heat up our little flask, things are going to evaporate, and then they pass down here, which has got cold water flowing around the outside. So it changes from a gas to a liquid, it condenses, and we collect it in our little test tube. So we would use our simple distillation, still with our salt water, but this time we want the water. So if we've got a solution and we want the solvent, the liquid out, we use simple distillation for that one. Key thing is that our solvent must have a lower boiling point than the solute. Otherwise, clearly it wouldn't work. The solute would evaporate first. Our next technique is another version of distillation. This one is fractional distillation. It comes up here and it's going to come up again when we come on to paper 2. What we see is we've got this device called a fractionating column. Can be a one marker for naming that thing on its own. So what we do is we heat up our little solution down here, and what's going to happen is it's going to evaporate, and again we're going to collect it over here. Now what we're doing with this one though is we're going to use a fractionating column, so we can use fractional distillation for a mixture of 2 or more liquids. Okay, so if we've got a couple of liquids that have different boiling points, we can use fractional distillation. Key thing, must have different boiling points, otherwise just doesn't work. Our final technique that we're going to look at is chromatography. Now we've got a range of different types of chromatography we're going to go through, but first one is the old favorite, which is going to be our TLC or paper chromatography. Okay, you've probably done paper chromatography at school. If you were lucky, you saw a TLC plate, but generally they're a bit more expensive, so they don't tend to give it to GCSE students. You tend to get the bit of filter paper, but they work in the same way. So what we've got, our plate or our bit of filter paper here. We then have our little pencil line, and we've got our little spot of our sample. We place it into a beaker or some kind of receptacle that holds a solvent, and then we wait as that solvent moves up the paper or the plate. So when we're doing this, there's a few things we should know. First thing, they can use this phrase called the stationary phase. The stationary phase is the thing that doesn't move. So if we're talking paper chromatography, the filter paper. If we're talking TLC, the thin layer chromatography, then that's going to be the silica or alumina powder on the plate. So those aren't actually moving. Instead, they are fixed, they're stationary, hence stationary phase. The other one, the mobile phase, this is the bit that does move. So what we actually find there then is it's going to be whatever the solvent is. So you can get around that in any TLC or paper chromatography by literally just writing solvent. Okay, you don't need to name the solvent, you can just go with solvent itself. Now, when it comes to looking at these chromatograms, the things we actually get, then you could be asked a range of questions around it. The first thing they could ask you to do is to calculate this thing called the RF value. So this is what we generate. And if they ask you to calculate the RF value, what we need to do is put our ruler on this pencil line where we started. And you're then going to carefully measure up to the center of whatever spot it is they've asked you to measure. We then do the same thing, ruler on our pencil line, and then up to the solvent front. So what we're then going to be doing is we're going to do the distance to our substance divided by the distance to the solvent front. That gives you an RF value. And to be honest, there's a really simple thing here, because what you can actually do is just common sense check. This is going to be a value between 0 and 1, and therefore, if you've got something bigger than 1, just flip the numbers the other way around. You clearly put them the wrong way around, okay? So RF value is always between 0 and 1, so literally If it's bigger than 1, turn them the other way around. The other thing they can ask you to do with our chromatogram is identify which substances are the same as one another. So that is as simple as match the patterns. So what we can see here is that A and C both have 2 spots and they line up beautifully. Therefore, A and C are from the same source. If they were to ask you which substance is pure, in that case it would be B, because there's only a single spot. And that is to the extent of what they're looking for as an answer for the justification, the explaining the reasons why. If they ask you how you know it's pure, there's only 1 spot there. If they ask you how you know they came from the same source, because the patterns match. That's all we're looking for on this paper. So we then have another type of chromatography we need to know about, which is gas chromatography. So here's our gas chromatography setup. We still have a stationary phase, which is going to be our alumina powder in this little coil down here. We still have a mobile phase, which is going to be the carrier gas. And what happens here is we inject our little sample and the gas basically pushes it through this little coil filled with the alumina powder. Different size bits are going to move at different rates, and therefore they come out the other side on the detector, get picked up, and then we get these little peaks on the screen. Still going to give us a way that we can identify different things based on when they come out. So smaller bits get out first, larger things take longer to get through. Now, if we are asked about comparing our chromatography, so the one they're going to ask you to compare here will be TLC to paper chromatography, then we can just remember basically 4 kind of key reasons why TLC is better. First one, it's quicker. Secondly, it's more sensitive, so that means that we can use smaller samples. Thirdly, we can have a greater range of the stationary phases and solvents to choose from when we're carrying it out. And finally, we can actually take that individual spot from the TLC plate, because it's just powder stuck on, you can just literally scrape the powder off, and then we can analyze it further later. So do bear in mind, when we're looking at those potential 6-mark questions where they're asking how you can separate out 3 different substances, the order matters. So not only do you have to actually identify which techniques to use, you've got to think about the correct order for them, okay? So you wouldn't obviously jump straight into fractional distillation if you've got bits of sand or something floating around. You do the filtration first. So think about the logical order for them, and there will always be a combination of processes involved. The next bit we need to know about then are the different metals and non-metal properties. So first thing, a physical property is a characteristic that we will observe or measure. So these are things like if it's malleable, so can we bend it? Is it ductile, so can we pull it into a wire? Chemical properties are going to be the ones that we can only work out through a chemical reaction. So this will be things like what kind of oxide we form. So our metal oxides, if we dissolve in water, will be an alkaline solution, but the non-metal oxides will be acidic solutions. We then come back to thinking about the periodic table, and hopefully we all know that the metals are all this stuff on the left-hand side. All of this is metals. The non-metals are these few on the right. If you can't remember that, literally just glance at the periodic table, find something you know is a metal, and you'll see if it's on the left or right, okay? So what we can do from that is obviously identify the position of metals and non-metals. Now, what we're then going to understand are hopefully that we've got vertical columns and horizontal rows with different names. So what we've got, first of all, our vertical columns are the groups. And again, OCR are rather nice because you know what? At the top here, they've actually given you the group numbers in brackets. So vertical columns are the groups. The horizontal periods going across, these are periods, okay? Go careful. The one people always miss is this top one here with hydrogen and helium. That is period 1. Here is period 2. So go careful not to miss the hydrogen helium first period. So We then have our basics on our periodic table. Hopefully we know that these elements are arranged into those groups, those columns, because they've all got similar chemical properties. And the reason they've all got similar chemical properties is because they've got the same number of electrons in their outer shell. Okay, so do make sure that you remember the group number tells us the number of electrons in the outer shell. The next thing we need to be able to do is draw these little sort of diagrams with our dots or crosses. And the first thing we need to do is the electronic configurations. Now, when we're talking electronic configurations, we're going to be using the periodic table to get the atomic number. And then from that, all we're going to do is draw them in the right numbers in the different shells. So we've got 4 rules, but we can actually only memorize 3 and get the right answer every time. If we remember that the shell that's closest to the nucleus holds a maximum of 2 electrons, the second and the third shell can hold a maximum of 8 electrons. Everything else goes in the fourth shell. You will be absolutely fine on the GCSE paper for that, okay? So 2, 8, 8 is the maximum numbers in each. Now, when we've actually drawn this, so if we just quickly sketch one out, so if we've got lithium, for example, we would have that as our little diagram. So we could represent that as 2.1, okay? So what we actually find then is the 1 tells us how many electrons are in the outer shell. That's also the group number. Because we've got 2 numbers here, then that tells us it's in period 2, okay? So you can actually work out what group it's in, what period it's in, just by looking at that number from the electronic configuration. Now, we're going to come on to our bonding types next. So the first type of bonding we're going to look at is ionic bonding. Now, ionic bonding is going to occur between ions, it's quite common sense, and this means it's always going to form between a metal and a non-metal. So quite simply, if you've got a metal joining with a non-metal, it will be an ionic bond between them. And the reason for that is the metals will form positive ions, the non-metals will form negative ions, and the ionic bond is this electrostatic force of attraction between the positive and the negative ion. Now, you can be asked to draw these dot and cross diagrams for the ionic bonds, okay? If we've got our basics here, okay, so I've drawn the actual atoms, we've got lithium and fluorine, then for an ionic bond, what's going to happen is we're going to transfer the electron from lithium's outer shell, it's going to lose it, and fluorine is going to gain it. So what we actually end up creating then when we draw our final structures, because they could ask you to draw a dot and cross diagram to show the bonding in lithium fluoride, for example, then one thing, make sure one is dots and one is crosses. Then what we need to do is make sure that we have got the little square brackets around it and the charge. So because lithium has transferred that electron across, we just draw that first shell with the 2 electrons, put it in the square brackets, it lost 1 electron, so it's got a +1 charge. Fluorine has gained that little cross from lithium, so it stays as a cross when all the others are dots, put it in the brackets, and put a single negative charge up there. So however many electrons are gained, that's going to be however many negative charges there are. However many electrons are lost would be how many positive charges there are. So don't forget to include those charges on there. Now, it is worth saying that if you are then asked to sort of do something where there's 2 of the ions of one type, you don't need to draw both of them. As long as you've got one of the positives and one of the negative ions drawn, you're absolutely fine for it. So, second type of bonding is our covalent bonding. And covalent bonding is going to be between non-metals only. Okay, so what we're going to be looking at here is 2 different non-metals or more than 2 non-metals combining. We will have a covalent bond between them. If they ask you what a covalent bond is, a shared pair of electrons is what we need to write down. Okay, now these are the ones where we're going to have our little intersecting circles. So carbon is in group 4, so it has 4 electrons, which I'm going to draw as crosses. Hydrogen only has a single electron in its outer shell, so they're going to share them between each hydrogen and the carbon. So this is one covalent bond, second covalent bond, third and fourth covalent bond. So wherever we draw a covalent bond, it's a shared pair. So there should be a dot and a cross. Don't forget we can have double bonds. So you might well find that you've got 2 dots and crosses in one of those intersections for some of those particular chemical combinations that we get. Now, don't forget when we're talking about covalent bonds and ionic bonds, they are both strong bonds, okay? The ones that are weak will be these intermolecular forces, okay? So if you imagine we've got oxygen, so this little oxygen molecule, then what we find is between each of those oxygen molecules, there are these weak forces, these intermolecular forces, and because they're weak, easily overcome, therefore it's got a low boiling point, hence why things like oxygen are a gas at room temperature. Now, the next thing we need to understand is the polymer. Okay, now polymers quite simply are made from many monomers and they will be alkenes. And what we find here is we're going to join lots of these little monomers together, and we need 2 conditions to make this happen: high pressure and a catalyst. This is what we call addition polymerization, and we'll talk about this again in paper 2 for chemistry. Now, they can ask you to name a polymer or to name the monomer. They will have to give you one of them for you to do this. And it's really straightforward as to how we can then identify the other. Because if we've got the monomer as ethene, then all you've got to do to make it into a polymer is write poly in front of it. It's that simple. If they've told you it's polyethene and they want the monomer, then literally just write down the bit that doesn't have poly. So whatever is left over that doesn't have the word poly in, just copy it and then you'll get it right every time. So to make a polymer, stick poly in front. To get the monomer, take the poly away. When it comes to actually drawing the displayed formula, again, they're going to give you the actual setup here. So they will have to give you either the monomer or the polymer so you can draw the displayed formula of the other one. So here's our little ethene as a displayed formula. If they were to ask you to draw the polymer of this, all you've got to do is copy it, but remember to swap out the double bond in the middle for a single bond, stick little arms out the outside, brackets, and a little N. So it really is that straightforward to get these. We've taken this, taken away the double bond, changed it for a single, and then just stuck little arms out the side in brackets with an N in the bottom corner. If they gave you the polymer and they asked you to draw the monomer, copy it, lose the little arms sticking out the side, no brackets, no N, and stick a double bond back in the middle. You'll get it right every single time. There really is no great complexity or challenge to doing that on this first paper. Sometimes you get questions about the different properties of our polymers because some are really flexible and other ones are really quite rigid in their structure. So what we actually find is that those ones that are really flexible tend to just have the individual strands. So they're just literally strands with these weak forces between them. The ones that are more rigid actually have these cross links. So they actually got a proper bond holding the individual strands. So that then means that if they've got a cross link, they're going to be more rigid in their structures. Now, the last structure we need to know about is going to be metallic. Now, common sense, metallic bonding occurs in metals, folks. If you don't get that right, I am sad. So this is our metallic bonding. To be honest, this diagram here is the one we really want to aim for. This one can come up as a little diagram, but I would never recommend you draw it. This is where we're going to go, okay? So if they give you a question that says, describe the bonding in a metal, then normally there's going to be a little blank space and then there'll be some answer lines. Because you can use a diagram if you wish. This is usually a 2-mark question and you can get both marks for a labeled diagram. So the label diagram would be having these positive metal ions have at least 6. So 6 circles with a plus in that we're going to label positive metal ion. And then we've got these little dots scattered around, which we will label delocalized electrons. If you do that, you've got 2 marks. If you want to be doubly sure and you want to double down on this, then what you need to do is just say that the metallic bond is the electrostatic force of attraction between the negative electrons and the positive metal ions. Electrolysis is coming up in C3. So we then need to understand a little bit about the periodic table and how we've actually come to have this thing we're all familiar with today. So the early versions of the periodic table had all of the elements that they discovered arranged in order of their atomic weight, not atomic number, atomic weight, because they didn't know what atomic number was. So they're all organized in their atomic weights, sort of in groups, but it wasn't perfect. Then this guy called Mendeleev came along, and he then did something a bit different. He still kept the atomic weights, but when he was actually putting them into their groups, he looked at it and then sort of said, you know what, these two here don't fit where their weights put them. I'm going to flip them the other way around because they fit better with those ones in those columns. He also said, you know what, there's something missing in this one. I'm going to leave a gap here for something we've just not discovered yet. So what that then meant was he actually left these gaps and he predicted the properties of those things. And what that means is he then had our modern periodic table pretty much sorted, even though not everything had been discovered, just by looking at the way that those different elements had reacted with one another. One thing that wasn't on his periodic table, initially anyway, were the group 0, the noble gases, for the simple fact that they didn't really react to anything, so no one really knew that they were there. So they came a little bit later, if you like. Now, the last little bit that we need to know about as far as our C2 topic focused on any particular aspect of our periodic table is carbon. Now, carbon is one of these kind of special elements, in all honesty. It's very versatile. It's actually got 4 electrons in its outer shell, therefore it can form up to 4 covalent bonds, either with other carbon atoms or with other elements. So when it forms these bonds with other carbons, all at solid state, then what we're referring to, the different way that they do this, gives us these things called allotropes. So an allotrope is just different forms of an element in the same state. Now, what we're going to do is have a look at a range of these different allotropes. So the first one is diamond. So diamond has got this kind of triangular type structure, and each carbon is bonded to 4 other carbon atoms. Now, because it's got 4 covalent bonds per carbon, this has a high melting point and it's hard. Because we have lots of strong covalent bonds which require lots of energy to break. It will not conduct electricity because there are no delocalized electrons. Our second structure is graphite. So we've got each carbon bonded onto 3 others. And in this case, what we find is we've got these individual sheets with these weak forces holding them together. So we do have a high melting point because there are many strong covalent bonds which require lots of energy to break. It will conduct electricity because that spare electron becomes delocalized. So we have delocalized electrons, and it's going to be slippery. So that means we can write on paper with it because those weak forces between those layers are easily overcome. So they just slide over each other. Our next one, which I haven't got a picture of because it's basically just one of these, is graphene. Now, graphene, to all intents and purposes, is a single sheet of graphite. And the key thing about our graphene is very strong, many covalent bonds, need lots of energy to break, etc. It conducts electricity because it has delocalized electrons, and it's almost transparent. So this is the thing they usually throw in about why would we use this in mobile phones? So transparent, we can see light through it. Conducts electricity so that obviously a touch screen actually works. Strong so that if you drop it, it won't break, etc. The last one we need to know about are the Fullerings, which are these carbon allotropes shaped like tubes or balls. And there is one particular one to know about, which is this one here, the buckyball. and you are absolutely fine to write the name buckyball. You don't have to write Buckminster Fullerene. I wouldn't recommend it either. Literally go buckyball. So that's 60 carbon atoms all joined in this sphere shape, and these could be used as lubricants, or we could use it as a drug delivery system. Package the drug inside, and then we can deliver it to a particular target. Now, when we're actually thinking about how we're going to discuss certain properties, then we need to understand why something is brittle or malleable. So when something is brittle, what that means is if we apply a force to it, then it's just going to snap, okay? So what we actually find is lots of bonds break at exactly the same time. So it's brittle. If it's malleable, then when we're applying those forces, all those little parts of it can slide over each other, and therefore it can change its shape pretty easily. Now, in terms of conducting, then we find anything with delocalized electrons can conduct, or if we're talking about an ionic compound, if it's molten or dissolved, it will conduct electricity because the ions are free to move. However, if it is a solid, then it will not conduct electricity for the simple fact that it holds those ions rigidly in their place. So that's one thing that you can sometimes do to identify the type of bonding. Look at the table they give you. It will have whether it conducts electricity as a solid, under molten, liquid, etc. Then the one that doesn't conduct as a solid but does as a liquid or dissolved, that's your ionic compound. Those of you doing GCSE chemistry just need to know this last bit of C2, which is about nanoparticles. So first thing, a nanoparticle is between 1 and 100 nanometers in size. And basically, these are things that we would use as catalysts. We can use them in things like sunscreen. We can use them on those self-cleaning windows and the like. And one of the reasons that they are so useful in a range of these is because they've got this really large surface area to volume ratio. We do need to be aware of some risks. So the key risks to know, they're really tiny, so you can breathe them in. They're so tiny they can actually pass through your skin, and they take a long time to break down in the environment, which is particularly problematic for the simple fact that toxic substances may stick to their surface, and then if it's going to take forever to break down in the environment, that means those toxic substances are going to be lurking around for a long time too. That's it on C2 then. So C3 is our last topic that we need to know about. So back for everyone combined and triple higher and foundation. What we need to know about, first of all, is how we're going to write a couple of key groups. So if we're talking group 0, the noble gases at the end, they only exist as a single element, okay? So they're going to exist as single atoms. You would literally just write whatever their formula is, so Ne, for example. If we're talking halogens, so group 7, these are what we call diatomic. So they always go around as a pair, okay? So whenever you write down any of the halogens in a balanced equation, you must remember to put that little subscript 2. If you don't put the little subscript 2, I guarantee you're getting 0 on any balanced equation involving a halogen. So what I mean by that is when we're actually writing any of the halogens, we've got that little 2 in the bottom right. If you don't do that, as I say, your formulas will be wrong, your balancing will be wrong. So that's a big 0 on any balanced equation involving the halogens. Now, we can use a nice simple little cheat in terms of working out the actual charges on the ions. Because if it's in group 1, it's a +1 ion. Group 2, +2 ions. And then on the other side, group 6 is -2, and group 7 is -1. You don't need to know the other ones in the middle there, okay? Now, one thing you can do, when they tell you in the exam tomorrow that you can start, you can grab your periodic table out and then add those little annotations. So quite simply, just write +1, +2 above groups 1 and 2, -2, -1 above groups 6 and 7. Then you've got it there right the way through. Now, what we do need to be able to remember are hopefully 5 of these things called compound ions. Now, compound ions are ones that contain more than one element, but they have a charge. So we've got the ammonium ion, NH4+, hydroxide, OH minus, nitrate, NO3 minus, carbonate, CO3 2 minus, and the sulfate, SO4 2 minus. Learn them, okay, because they could ask you to write a formula involving any of those compound ions. If you don't know them, it's clearly not going to go too well there. When we then come to write an ionic formula, so when we're putting two ions together, the key thing here is we've got to make sure that the charges balance, okay? So if you've got one positive, one negative, then they just join 1 to 1. If you've got two positives and one negative, then you're going to need two of those negative ones per positive to cancel out those charges. So just make sure you look at the charges and get the right numbers in there. Next bit is the law of conservation of mass. Quite simply, this is just a law to know that because atoms cannot be created or destroyed, the mass of your reactants must be the same as the mass of the products. So what they can ask you here is they will give you the masses of, say, 3 out of the 4 things in an equation and ask you how much of the other one we've got. So add up your reactants and then subtract that odd product. Whatever's left over must be the other one. Works either way, as long as we know that obviously we add up the reactants, add up the products, and they've got to be the same on each side to get it. The one that they typically ask about that in practical terms is that they'll be talking about something that makes a gas and why that's not going to be true. And for the simple fact is because if we don't have a closed system, i.e. something with a lid on it, then the gas is obviously going to be lost to the surroundings, so you see a decrease in mass. We then need to know how to obviously write word equations. Use the full names. Please don't abbreviate to symbols because it is a word equation. Balanced symbol equations, which is where we're going to obviously use the chemical formulas and then balance it. Typically, 2s and 3s are going to be the things going in there. And then we also need to know about state symbols for these. When we're talking about state symbols, there are 4 you need to know. Solid, lowercase s in brackets. Liquid, lowercase l in brackets. Gas, lowercase g in brackets. And the aqueous solution is a lowercase aq. If you're doing the higher tier on either combined or triple, you need to know about these half equations and ionic equations, okay? So what we actually find is that a half equation is basically just modeling the change that happens to a single reactant, okay? So we're not looking at the whole thing, we're looking at just one of those reactants, okay? If we were to be looking at something like sodium, for example, then what we would have is a sodium atom, so we'd have Na on one side, and on the other we'd have our sodium ion, Na+, and we'd have our electron, E-. So wherever we're using electrons, always lowercase e with a little minus sign. We're basically just shoving electrons in to show how we get the different ions. That's pretty much what these half equations actually are. If we're talking ionic equations, then quite simply what we're doing here is we're going to look at the equation, we're going to look at all of those ions that are present, and then any that are the same on the reactant side as they are on the product side, we just ignore. They're spectator ions, we don't really care what they're doing. That leaves us with the ones that are doing something different. We then write that, and that gives us our nice little net ionic equation. And to be honest, the one that really you should look out for, and this comes up in the electrolysis section as well, is that we're going to look to see how we actually make water. So look out for this one. H plus OH minus makes H2O. That's probably going to be one of the more common ones that crops up there. Still higher tier folks only, we need to know about the mole. When we talk about the mole, this is the amount of substance that contains the same number of entities, and an entity is an atom, an ion, a molecule, as there are atoms in 12 grams of carbon-12. So its units are mole, MOL, and the other little value we need to know about for some calculations associated with this are Avogadro's constant. Now, Avogadro's constant is the number of entities in 1 mole, okay, and that basically has a specific number, 6.02 times 10 to the power 23. There's no guarantee they're going to give that to you on the exam paper. Sorry. So 6.02 times 10 to the 23. What you would do if they were to ask you how many molecules there are in 4 moles of water, for example. All you then do is 6.02 times 10 to the 23 times 4. The one to watch out for here is where they actually say how many hydrogen atoms are there in 4 moles of hydrogen. Now, because hydrogen is H2, what people tend to do is 4 times 6.02 times 10 to the power 23, and that's what they write as their answer. That's molecules. Because there's 2 hydrogens, you've got to then times it by 2. So watch out for them being a bit sneaky there. If it says atoms, look carefully. Still higher tier, folks, we need to know about the molar mass, and quite simply, that is the mass in grams of 1 mole of a substance. It's the relative formula mass again. Just add it up, you've got it absolutely fine. Then we come on to the mole calculation stuff. So what we're going to be using is our mass in grams is the molar mass times the amount. So what we can do is we can generate our nice little triangle again. So when you've got your triangle, you're going to have mass in grams at the top, molar mass and amount at the bottom. If you know that formula, you are going to be able to work out these mole-related calculations, because it's just rearranging that formula based on what you've actually got, okay? So the way these mole calculation works is you're going to start off by reading the question. It will tell you a mass in grams of something, and then it will obviously have what you need to work out. So you've got 2 chemicals that you're going to be concerned with. One, you've got the mass in grams of, the other you're going to be calculating the mass of. So first thing to do, work out the molar masses of those 2 chemicals, write that down, that's usually your first mark straight away. Then you're going to work out the amount in moles, which is just the mass in grams from the question divided by the molar mass of that particular thing. And then we're going to look at our balanced equation that we've got and just compare the ratios. So if it was a 1-to-1, but in your calculation you only had 0.5 moles, then you would have 0.5 moles of the other. If it was 2-to-1 and you had 0.5 here, then obviously you'd have 1 mole of the other. Keep those proportions the same, you've then got that next bit. All you can then do is shove that back in. We've got a molar mass, we've got an amount in moles, multiply those together, you've got the mass in grams. Those mole calculations aren't as scary as you think. Just work through it in that simple step. Molar masses first of all, work out the amount of the thing you can, then you do your little comparison using the balanced equation, and then stick it back into the rearranged equation. Job done. So back for everyone now, we're on to our exothermic and endothermic reactions. So combined and triple, foundation and higher, folks, you all need this bit. If we are talking an exothermic reaction, this is one where the temperature increases because we are giving out heat to the surroundings. Think combustion, neutralization reactions. On the other side, we have endothermic reactions. These are where the temperature is going to decrease, and this is where heat is being taken in from the surroundings. Photosynthesis is the one that we overlap with biology there. Now, what we actually find, the reason for this is because during a chemical reaction, we're transferring energy. So energy is going to be transferred from the surroundings to break these bonds in the reactants, and then to the surroundings when new bonds form. And what we're then going to do is basically compare the difference between them that then gives us whether it's endothermic or exothermic. Now, associated with this, we will be asked potentially to draw or interpret one of these reaction profiles. So a reaction profile, quite simply, is a simple diagram showing us the energy changes in the reaction. Horizontal line for the reactants, horizontal line for the products, and then there's basically this little humpy line that connects the two together. Now, you'll notice that depending on whether it's endothermic or exothermic, the lines are in different places. So in an endothermic reaction, the reactants are beneath the products. In an exothermic reaction, the reactants are above the products. There are 2 things you need to be able to label on this. So activation energy, first of all, you're going to have a nice little line that goes, you can see over here, from this little area here to the top of the little peak, okay? Please draw it carefully, don't rush it, because if it's given you these to draw, then you need to make sure it's a nice vertical arrow, the bottom lined up with our little reactant line, the top lined up with the top of the peak there, and it's labeled obviously activation energy. The energy change is the difference between the reactant line and the product line. Again, draw it carefully, a vertical arrow going level with the bottom of the reactants and the products line. Don't rush them or you're going to throw away those marks, okay? Now, activation energy, they ask you what it is. It's the minimum energy needed for a reaction to start, okay? So, what we then need to do on the higher tier is know about how to calculate these energy changes. So what they would do on this kind of question is they'd give you a little table with different bond energies. You would then have to work out what bonds are present in each of those reactants, each of the products. Usually it's going to be split into 3 sections. First section, calculating the energy required to break the bonds in the actual reactants. Use your actual little displayed formulas, look at the bonds numbers, use the energy levels in the tables, multiply them, add them together. Then you do the same thing for your products, obviously looking at your displayed formulas, using the bond energies from the table, and then adding those up. And the final one is the energy change. Now, lots of people look at this and think, I don't know how to do this, I'm going to leave it all blank. Stupid, because the reality is, even if you don't know the first 2 things, if you've written a random number on the answer line in those 2 sections, and then done the subtraction at the end, you got the last section right, because you get these error carried forward marks. So if you can't think how to do it, doesn't matter. Stick any old number you like on the first part, any number you like in the second part, and then it's just reactants minus products for the third part. You've got that bit anyway. So you won't throw away all the marks, you can at least get some. Just make sure, obviously, you do write the numbers in there. You can't just write random numbers in the third section and get it. When we actually have calculated those energy changes, if it's negative, it is exothermic. If it is positive, it is endothermic. Right, back for everyone again then. So this is for the foundation, the higher, and the triple and combined folks. We need to know about redox reactions. So redox reactions are where we have both a reduction and an oxidation happening at the same time, okay? If we're going foundation level, then reduction is the loss of oxygen and oxidation, the gain of oxygen. If we're going for the higher level, then they're talking electrons. So this is where we go to oil rig. So oxidation is the loss of electrons, reduction is the gain of electrons. The one other thing they can throw in here are reducing agents and oxidizing agents. So a reducing agent is the one that's going to gain the oxygen. The oxidizing agent is the one that loses the oxygen. Just watch out for that one because people often do make errors on that one. We then need to know something that again goes back to Key Stage 3 in our lovely Year 7 course of the pH scale. So hopefully remember the pH scale is that 0 to 14 number scale, and if we add universal indicator, we get pretty colours. So acids are going to be less than pH 7, so that's the 0 up to the 6.9 basically. And with universal indicator, they are red, orange, yellow colours. These are the ones that are going to release hydrogen ions when they're in a solution. Neutral solutions, they're pH 7, they're green with the universal indicator, and then our alkalis greater than pH 7, they're going to be blues and purples, and these will release the hydroxide OH- ions when they're dissolved in water. In terms of how we measure pH, another practically type question they can throw in here. Yes, we can use universal indicator solution, but it's a bit rubbish because, as you probably know, where you've been sitting there trying to squint at that terrible little bit of printed card, matching the colours doesn't always go well. So that means we've got a bit of a problem because it's not easy to match those colours. How can we improve it? Use a pH meter. So quite simply, all we're going to do, get a pH meter, you're going to calibrate it using a buffer solution, and then you just place it in your test solution. Push the little test button, and it gives you a little readout on a screen. Far more accurate, number one, because we're not having to interpret colours. Number two, these usually go down to a decimal place or two as well. So the typical reaction we're going to look at with our acids and alkalis will be neutralization. So acid plus alkali makes a salt and water. Hopefully you remember that from, again, Key Stage 3. What we're going to find is the reason that we make that water is the acid is releasing those hydrogen ions, the base or the alkali is releasing the hydroxide ions, so they join together, we make water. Salt is basically the other stuff. Now, you've got to be able to name salts, folks. So for this, we need to remember two basically simple rules. First one, the first word is always going to be the metal. So whatever the metal is, write that down first of all. That's the first word of the salt. The second word in the salt comes from the acid. There are four you need to remember here. Hydrochloric acid makes a chloride. Sulfuric makes a sulfate. Nitric makes a nitrate. And phosphoric acid makes a phosphate. So if you had, sodium hydroxide reacting with sulfuric acid, we would make sodium sulfate. First word is the metal, second word from the acid. That's straightforward as long as you remember those four different endings from the four acids. Next reaction we need to know about is carbonates and acid. So metal carbonate plus acid is going to make the salt again, going to make water, but we also make carbon dioxide. And carbon dioxide we can test for using lime water, which goes from colourless to cloudy. Please use the word colourless. Don't say clear. Clear is not getting you a mark. Clear means there's no bits floating in it. Colourless means it is lacking in colour. And that is what we have here. Something that is colourless and it goes cloudy. You can say milky as well there. Third reaction with our acids is the metal and acid. So this is where we make the salt and hydrogen. Test for hydrogen. Lit splint makes a squeaky pop sound. Make sure you do say it's a lit splint, not a glowing one. Otherwise, it just won't work. For those of you doing the higher tier, then we need to know about concentration as well. Okay. If we're talking about a concentrated solution, then this is one that only has a very small amount of liquid dissolving the solute. If we've got a dilute acid, then basically we've got a lot more liquid dissolving that solid. So what we're looking at is a low ratio of the acid to the volume of the solution in the dilute one. There's a second phrase we associate with our acids here, which is to do with strength, not the same thing as concentration. So what we're looking at here is you either have weak acids or strong acids. A weak acid is what we call partially ionized. So that means only some of the hydrogen ions have actually been released from the molecule. The strong acids are fully ionized, all of the hydrogen ions have been released. So make sure you know the difference between concentration and strength because they are two separate measurements. Now, the last little bit to do with the pH that we need to know about here is a calculation bit for higher tier folks, which is that when the concentration of hydrogen ions increases by a factor of 10, the pH decreases by 1. So if we had the concentration of hydrogen ions going up by 100, then that would mean we're seeing 2 steps of pH reduction, because obviously 10 times 10 gives us 100. So just make sure you remember each factor of 10 is a pH decrease of 1, and that means you can then work out the new pH of your solution. Right, back for everyone for the last bit of C3 and the last bit of the paper tomorrow. We're on to the fun-filled electrolysis section that so many of you seem to hate for some reason. Now, electrolysis is using electricity to split a chemical. Electricity, lysis, splitting stuff. So basically, we're going to use electricity to split things. In order to do this, we are going to need 2 electrodes. They may be made of metal, may be made of graphite. We need an electrolyte, which is a liquid or a solution that is going to allow the mobile ions to move through it. And finally, we need some kind of electrical supply. First thing, we need to know the names of our electrodes. So there is a negative one and a positive one. The negative electrode is the cathode. The positive electrode is the anode. So make sure you know the names and the charges, if nothing else to do with electrolysis. Then in terms of what's attracted to them, opposites attract here. So our cathode is negative, so it attracts the positive ions. The anode is positive, it attracts the negative ions. So basically, as we pass the electricity through, our little solution here, the electrolyte, then what's going to happen is we've got our negative electrode, the cathode here, all the positive ions are going to go to this side. Then we've got our positive electrode, the anode, all the negative ions go to that side. So that's the basics of how electrolysis works. We're literally splitting using those opposite charges going to those electrodes. Now, they could ask you what we're going to make when we're using electrolysis with different things. First one is straightforward. If we've got a binary ionic compound, i.e. an ionic compound made of only two things, one will be positive, one will be negative. So they literally just go to the oppositely charged electrodes. So the metal is going to go to the cathode and form there, and the non-metal bit is going to go to the anode and form there. Really straightforward. Just remember that it can only happen with those ionic compounds when they're either dissolved or molten, okay? If they're solid, it's not going to work, all right? If we go slightly more complicated, we've dissolved this into a solution now. So we've got a solution of something, which means we now have competition at those electrodes. Because if it's a solution, we have water, which is going to be split into hydrogen ions, H+, and hydroxide ions, OH-. So we've basically got two positive ions and two negative ions that will compete because only one can be discharged at the electrode. In terms of what will form then, simple couple of rules to remember. So the first one is that at the cathode, we will form hydrogen unless a metal that is less reactive than it is present, okay? So that means if we've got copper, silver, gold, or platinum, they will form. If we don't have copper, silver, gold, or platinum, then hydrogen is going to form. Justification for that is that it's only when the metal is less reactive than hydrogen that it will form. On the other side of the anode, or positive electrode, it will be oxygen that forms unless we have an element from group 7, the halogens. If there's any group 7 present, then it will form at the anode instead. And remember, you've got a periodic table, so you can always check it. So we then need to understand a process we call electroplating. Now, this is basically where we're using non-inert electrodes. Usually in electrolysis, we use inert electrodes because they don't react. But in electroplating, we use non-inert electrodes because they do react. We want them to react. So what we're going to find here is our cathode is going to be what we want to coat. The anode is the metal we want to coat it with. And our electrolyte contains the coating metal. Okay, so it's a solution that contains that particular metal. Now, what happens here is when we flick our little switch on our current, then the metal ions are going to then become discharged on the surface of the object, and therefore those metal ions on our anode get released to replace the ones we've lost from the solution. So basically, we're transferring the metal from the anode through the solution to be deposited on the material at the cathode, and then we build up this coating. Hence, it's electroplating. We are plating it using electricity. They could ask you to write half equations for these ones. So again, if you're on the higher tier, just look and see what we're talking about on that electrode, and then where are the electrons being gained or lost from. That's all you've got to do with those half equations. Final thing is just how we look at purifying something. So if we're looking at purifying copper as the typical one they go with here, then our anode is impure copper, cathode is the pure copper, and we have copper sulfate solution as our electrolyte. Flip the switch, and all that's going to happen is the anode is then going to have the copper transferred across to the cathode, and any of the impurities sink to the bottom and collect underneath as the sludge. And that is the entirety of C1, 2, and 3. So that is, in theory, all of the facts you need for tomorrow. So I saw someone in there ask a question about why diamond is so hard. And the reason for that is it has lots of strong covalent bonds that require lots of energy to break. So anything to do with why it's hard or why it's got a high melting or boiling point, lots of strong bonds, name which one it is, that require lots of energy to break. So tomorrow, make sure you take a calculator, make sure you take a ruler with you, because obviously we could find any of those questions involving calculations and measuring bits, and then use that periodic table, folks, okay? Don't just leave it sitting there untouched, otherwise that's really quite ridiculous. Okay, so that's it for tonight. Obviously, do make sure you go over any bits you're not 100% certain on, and good luck tomorrow. We will be back on Wednesday at 6 o'clock for physics. So the physics one is obviously going to be the paper one. If you're doing combined science, that's units 1, 2, and 3. If you're doing the triple physics, then that's 1, 2, 3, and 4. So I will hopefully see you all on Wednesday. Good luck tomorrow, folks.